Welcome to class 2 of ISSS course on computational physics with Python. So we'll resume from where we left off last day. And so this is question number 7 from, again, assignment 1 from the same GitHub repository which we were doing. Okay. And I'll just read the question and then we will proceed just like before. So the Catalan number Cn are a sequence of integers 1, 1, 2, 5, 14, 42, 132 that play an important role in quantum mechanics and the theory of disordered systems. They were central to Eugene Wigner's proof of the so-called semicircle law. They are given by this number. Write a program that prints an increasing order of all Catalan numbers less than or equal to 1 billion. So it just gives you an iteration that you start with C0, which is equals to 1. So once you know C0, then you can keep on going through this iteration, and this gives you C1. And then once you know C1, you get C2. You keep on doing this. And it says that you have to print all the Catalan numbers until you get to 1 billion. So it's, I would say, a fairly straightforward problem. So let's get started writing this. Okay. Just like before, we will be using NumPy and get rid of the code from the last week. And we will minimize this as well. Okay. So I will start sharing my screen. Yeah. Is my screen visible? Is the screen share working?
Yes, it's visible.
Okay. So as I was saying, I will get rid of the code from last week. Just keep the NumPy because we might use that. It's so useful. And let's write def data. Let's call this function again, and we will be giving cn. So we'll have something like cn, which is a float, and we'll also have n, which is an integer number, right? And this will give me float in return, which is another Catalan number, right? And then what we will do is use the formula for Catalan number. It's 4n plus 2 divided by n plus 2. Okay. So you'll see n plus 1 is 4n plus 2 4 times n plus 2 divided by n plus 2. So these brackets are important because that determines the order in which this has to be done. Otherwise, it will not be done properly. And then we have this cn, right? And after doing this, we'll just return cn plus 1. Okay. So now it says that we will be starting with a Catalan number C0, which is equals to 1. Oops. 1, and then keep on iterating through it. So so we will give something like call something like C next is equals to, say, start with something. This is really a dummy number, which we will start with. And once we have done, we do while C next. So this is like every time it will be using C next. And we will be doing it till it is equals to 1 billion. So it shall be less than or equals to less than or equal to 1 billion. Okay. This is 100, this is 1,000, it is 10,000, so 100,000, a million, 10 million, 100 million, and a billion. So there's many zeros. 2, 3, 4, 9. So there are 9 zeros. So we can also like type just a 0. Yep. So any of the two will work. And we do this, and we can call C next equals to, and our n is equals to 0 to start with, right? So C next is equals to, we'll call Catalan. And for Cn, we will give, this has to be C0. So that's what we start with. So we call it with C next and n. And then n has to now increase with 1. So this n plus equals to 1 and n equals to n plus 1 both means the same thing. So I generally prefer this because it's just straight like a shorthand, but you can do whatever you like. Okay, and then once this is done, I come out of the loop and print in F strings something like C n. So remember that this is increasing by 1 every time, and then it checks. So the last n has increased, but the number which we have gotten is n minus 1 because we did not do the next calculation. So first it was 0. So what we have got is, wait a minute. No, actually not. First is 0. So if it comes out of the first loop, then it's 1, and C next is C1. Yeah, I think this is right. And then this is C next colon 0.3 E6. Yeah. So this is it. So let's try to print this. So yeah, you see C19. So it got to 19 iterations, and it has given me something which is greater than. So I think, okay, got it. What has happened? So it then checks, and I want something which is less than or equals to 1 billion, but you see it has gone over 1 billion. So actually what we want is C18 instead of C19, because C19 already goes over 1 billion, and then this check fails, right? So then what we would do is we'll come out of in here, and we will do n minus equals to 1, because we want it has already crossed 1 billion, so it's a previous number that we are interested in, right? And then let's see. There is some way of keeping track of the previous number as well. So, okay. We do something like C old, call it C old. This is C next. This is again C next, right? And then sorry, this is C next must be equals to C old, and to start with C underscore old equals to C underscore next, right? So what we want here is the previous one. So it's Cn minus 1 and what we will be interested in C old. Right. Okay. So let's see what this was doing. So what this does is when, okay, I can just start with a breakpoint, so that will be much easier to show. Let's first check if it is working or not. Yeah, this now gives me C18, gives me the correct number. So now let me discuss what is actually going on in here. So let's have two breakpoints and start the debugging. So here, once I go in, I start with C0 and I initialize my C next with C0. So this is what my starting point is, and n is obviously 0. So as you can see, these variables get created in here. Now we go into the while loop. Oops, sorry, I stepped twice. Okay. Let me stop this thing and restart this. Yeah. I go in here and you see this is cold. So now what this will do is this will create a new variable called cold and put the same value as cnext. So here now cold, everything gets the value of 1. Now I will call Catalan, which is now going to get me the next Catalan number with the new value of cold. All right. So this will give me the next Catalan number. So n is 0 and cold is what it was corresponding to. So the cnext is going to change. So cnext has changed. And as you can see, cnext changes to a new number in here. And then n updates to 1. So n from 0, n changes to 1. As you can see in here, now n has changed to 1. Now it compares cnext. Now if cnext is less than 1019, which it is, it goes to the next step. Now cold is again assigned the value of cnext because now this is the new old, because now we are going to generate the next number. So before we generate the next number, we are assigning the previous value in cold, just so as to keep track of what was the previous value. So that we do in here. And now we again generate a new Catalan number with the value of cold, and that reassigns the value of cnext. So you see the cnext got changed, and as you can see, it became 2. And now n will become the new value as well. So n becomes 2. Again, the value is checked. Again, the new now the new cnext becomes cold before I change cnext. And now I'm changing cnext to the value with the value of cold. And as you can see, now it becomes 5. So this goes on and it is again updated, and we will keep on doing this until you see it becomes large and large, and now it increases a lot after a while. And then once we hit something like around 19 or so, as we're seeing in the code, let's go in there, 17, 18. Yeah. So now you can see the value is very large, and now we have a cnext, and then n increases. And this is, I believe, the last time we go in here, cold again gets the value of cnext. And now the cnext, the new value of cnext crosses 1 billion, and n is obviously increased. Now, since it has crossed 1 billion, the while loop is now comes out of the while loop, the code. And therefore, what we need in here is the value just before 1 billion was reached, because we want a value which is just less than 1 billion. So that corresponds to now the previous Catalan number. So to cn minus 1 and cold is the corresponding value that we have got on it. So that is something which gets printed in here. And as you can see. So is this clear?
Yes, yes, it is clear. So I was thinking that can't we implement this function in a more recursive way, like since cn plus 1 is represented in terms of the cn, so directly from within the Catalan function we could have returned the values of
Yes, yes.
somehow.
Yes, there is a functional recursion thing. I think I will cover functional recursion, but I want to start with functional recursion with a something simpler than Catalan number. So what I'll have planned is I will talk about recursion while talking about factorial and also Catalan number as well, but in a exercise or in a question which is coming up next. So for now, I kept it simple. They didn't have recursion of functions, but that is something which I have planned to cover, like after a few questions.
Okay.
Okay. So then next, let's go to the next question, which is about this Madelung constant. So idea here is that you have a potential which is due to an alternative in a sodium chloride crystal. So you have sodium and chloride and alternating ions of positive and negative charges. And the idea here is to find out the potential at the origin. And it turns out that this gives rise to a series where you have three indices I, J, and K. And when this, like if you think of a crystal which is perfect, it goes till infinity. So in principle, we cannot go till infinity. So we'll go to a large number and try to find out what would be the potential at the center of this crystal, which is infinitely extending. Right. And since the crystal is infinite, you can think of the same potential as everywhere. Now this is becomes translationally invariant as well. So this is the potential at every point in the crystal, which is there due to the electric field created by these positive and negative charges, which is due to sodium and chloride ions. Okay, so without going into the detail, I think I would highly encourage you to read this question. It's fairly descriptive, and it would be, I think, quite easy to follow, but I'll just simply use the formula of Madelung constant, which is without the prefactors, 1 by square root of I square plus J square plus K square. And then we will do like a sum of all the values of I, J, K so that we get to the value. Okay, so let's call, so as it was there, so I in range. So we will call L to be a large number. So, and as you can see in here, the L runs from minus L to plus L. So let's call L to be, say, 100. I mean, this is just a number. The larger you make, the better you estimate the Madelung constant. So it converges with larger and larger value of L. So we'll start from minus L and go till plus L. So this is L plus 1. So one thing to note in here, what happens in kind of a range function in Python is that it goes till the value less than 1 less than what you give at the end. So just to give you an example, let me clear the terminal in here to make it clear what I mean by this. So for example, you can like for test in range. So you start from say 5 and you want to go till 9. So then you have to give 10 and then you give the step number. So you increase by plus 1. This is optional. If you do not give anything and if you do this, then it also means by default increasing by plus 1. And then if you do print test, and so you see what is happening is you start with 5, but you end in 9. So because you end at 1 less than what you give. So that's why if I want to start with minus L and end at plus L, I have to give something which is 1 more so that I end at plus L. Okay. And I can give up 1. I can choose to omit it out, but it gives the same thing. So this is by default. If you want to have a step which is different, then obviously you need to change it. So let's say, for example, this gives you 1, but you can change this to 2, and then this will be at steps of 2. So 5, 7, 9. Yeah, I hope this is clear. Okay, so we go do this, and similarly, we do the same thing. So there are 3 numbers in here, so we'll do the same thing and change this to J and change this to K. And let's call M. M is the Madelung constant, which we are dealing with. And let's say start with 0, right? And you have then the sum, right? And the sum is just the plus and minus of the thing. But let's see formula of this. The sign on the expression depending on I plus j plus k is odd or even. Okay. So now the first thing is here you have I. So both I, j, and k should not be equals to 0. So if I equals to 0 and j equals to 0 and k equals to 0, this case is not, I mean, allowed. So we pass it. So by pass, I mean, you do, sorry, not pass, but continue. So continue the loop. So do nothing, right? But else you do something, which is where the Midland constant will be done. So we will also check the sign. So the sign is whether it's positive, odd or even, right? So that will be, so remember that if anything, -1 to the power of I plus j plus k. So what this would do, this value, is that if I plus j plus k is this sum, if this is even, then the value that then the output of this thing, which I'm highlighting in here, is going to be positive, because we know that -1 to the power of any even number is +1. Whereas if -1 to the power of any odd number is -1, so then what this would mean is that the sign will be negative. So this is the prefactor that comes with the Midland constant. And along with that, we do a square root, right? So that will be slash, we'll use numpy.sqrt. We do something like I square plus j square plus k square. And this is all that is there to it. And then we'll do something like m plus equals to this, right? So let's start with a smaller value of 10. So we'll keep on increasing this value now after every run and see, do we have convergence? By convergence, I mean that with increasing L, does the value close into some particular number? Okay, let me just removing all the variables and let's just print m equals to, this is the Maitland constant, colon 0.5 f, right? So this is what we do. And then let's start the code. And we see that we get something like minus 1.695258. So let's increase this to a value like say 100. It will take a while because now the code takes a lot of time to complete because the loops are large. So every time it goes to 100, so it will be 100 times 100 times 100. So it is quite a bit of code work. So you see that the value has changed, but let's see if we keep on increasing this, do we go to a number which is closer and closer? So I'm just waiting for the code to finish. It takes a while because there are 3 loops involved in here. Oh, it takes really a long time.
So I have a question here that why do
Yeah.
we why do we use NumPy? When do we use NumPy?
Oh, so NumPy we are using for finding out the square root, but I mean, you can also do something like, say,
So, like say math dot square root kind of thing,
or you
or
can do something like this. This will also work.
yes. But then I was under the impression that we use numpy for the arrays. And there is, in this case, we are using the function of the numpy np dot square root even for a single element. So single
Yes.
element, yeah, okay, how is that possible?
So NumPy is pretty agnostic to whatever you give, you get that output. So if you give a number, NumPy gives you a number. If you give an array, NumPy gives you an array. If you use something like a math library, you cannot use an array in it. So the advantage of this with NumPy functions is that it is vectorized. For example, say if you have an array of 10 elements and if you want to find out the square root of it, then you can directly pass the array and it will do give find out the square root for every element and give you an array back. So you do not have to have a for loop. So that's the advantage of NumPy. Here, the advantage is not realized, but that is really the advantage of using NumPy. And so that you can avoid for loop. And what happens in this case is that there is always a for loop which goes under the hood. You do not have to care for it. And NumPy, these functions are actually implemented in the backend in C or C++. So that's very fast. So in general, what happens is in Python, loops are very slow, as you can see in here. So executing loops takes a lot of time. So if you can somehow bypass loops, that's the best thing. And then the looping part is handled by C or C++, which makes the code really fast. So it's therefore advisable to use NumPy when you have large arrays, which is not the case in here, but you can still do it in this case as well.
Okay,
Okay, so as you can see, this Medlang constant, it gradually converges to one particular value, which is around minus 1.7. So I changed from, this was with 10, then this was with 100. There is a lot of change. Then with 100, with from 100 to 200, there is not much of a change. So we know for sure that these three values are I have converged. This I have not. So we have to, if you want to be sure about what is this value or what is this digit, then you have to use more and more value of larger and larger number L. So, but there is clearly a convergence which is happening and the value is converging to a particular value. And now depending upon up to how many digits you want to find out the value of Magellan constant, you will get a better and better estimate. This is similar to like up to how many decimal points do you want to find out the value of pi. Is something similar to that. So I hope this is clear. Cancel. Let me call this actually session 2 because today is a session 2 in here. And make this large, just like this one. And let's copy this and paste it in here. Okay. So this is just the Magellan constant thing that we have done. And I hope this was clear to you. Let's see. Let me make it a little bit smaller. Oops. I did not want this. What did I do? Let me close this. I have used some shortcut, I guess. What's let me try to figure this out. I'm stopping the share for now, and let me try to figure this screen layout, and I'll be back. Yeah, I guess I have been able to figure this out, what has happened. Okay. So I had accidentally created two panels because of which this has happened. But anyways, no, I think we are good. So we are now back to this midline constant thing. And just confirm that the font size is legible, right?
Yes, yes.
Okay, okay, great. So let's then go to the semi, that's the next question about the semi-empirical mass formula. First, let me clear this out for the time being. Yeah, in semi-empirical mass formula is a formula for calculating the approximate nuclear binding energy B of an atomic nucleus with atomic number Z and mass number A. And this is the formula for which, where in units of millions of electron volts, the constants are A1 is this, A2 is this, A3 is this, and A4 is this one. And there is a value of A5, which depends on certain conditions. So now what this says is that write a program that takes as inputs the values of A and Z and prints out the binding energy of the corresponding atom. Use your program to find the binding energy of an atom with A58 and Z28. Okay, so let's try to do this. So let's first then write a function, def, we call it, say, binding energy, BE or BE, something like this. And then it will get A, which is an integer, and B, Z, which is also an integer. And we'll give something like a float because it's a binding energy which we want. And that's it. So now we have to get these constants. So A1 to A4 are pretty simple. You just write the values. This is, sorry, 15.67. A2 equals 17.23. A3 equals 0.75. And A4 equals 93.2. Right. And then we have to find out A5, which depends on what A and Z are. So we'll have to give a condition. If A, so if A is odd, then it says 0. If A and Z both are even, then it's this. And if A is even and Z is odd, then it's minus 12. Okay. A is even, both are even. Okay. So we do a percent 2 equals to, so not equals to 0. So that would mean what this percentage does is finds out the modulus. So modulus is the remainder of a division. So this, if I divide by 2 and the remainder is not equals to 0, then I know that a is odd. And now it says that if a is odd, then a5 equals to 0, right? Otherwise, we check both a and z are odd or not. So let's do this. We do else. We go in here and we check if z is even or if z is odd, right? Because a is already even if it is else. So if z percentage 2 equals to 0, that means z is even, then we know that a5 equals to plus 12, as it says. Else, if a is even but z is odd, right? So it will be an else as well. A5 equals to minus 12.0. So I think this is what the constants are. So now it's relatively straightforward to find the binding energy. So we call binding equals to A1 times A minus A2 times A to the power of 2 by 3 minus A3 times Z square divided by A to the power of 1 by 3. So there is something in Python which you can do is something called line continuation. You can keep on writing the thing in here, but sometimes if you have a very large line, you can do this slash, which is the front slash. I guess this is called, or this is called backslash. Something, I mean, not the division sign, but the other one. And then you can continue writing the same line from the others, like give an enter and continue writing from the other line. But it is considered as the continuation of the same line. So A3, and then it's A4. So they do a minus A4 times, so let's do the same thing. A4, I'm just trying to align it just for that it to look good, but yeah, nothing sacrosanct about it. A minus twice Z whole square divided by A, plus the last term is A5 divided by A to the power of half. So basically square root of A, but anyways, let's write whatever, however it was written in formula. So let's first verify. It's A1 times A minus A2 times A to the power of 2/3 minus A3 times Z square over A to the power of 1/3 minus A4 times A minus twice Z whole square by A plus A5 divided by square root of A. Yeah. So once this is done, what I'll get is I'll return binding. So this is the binding energy formula. So now let's go and check this question where it says that to find it out for A equals to 58 and Z equals to 28. So let's define a value of A, which is equals to 58. and Z, which is equals to 28. And then let's print we'll again call it an F string, and we'll call BE equals to, we'll call the function in here. The function is BE and A comma Z is the function that we are going to call. And this will be, say, 0.1F, right? And this will be in mega electron volts, so MeV, something like this, right? So this is what we are going to print. And let's see. So yeah, we get something like a 493.9 mega electron volts, which is close to 490 as the question says. So this part is okay. Now it says modify your program to print out not the binding energy, but the binding energy per nucleon, which is B by A. Right. So this is very simple. So we'll just create def binding energy per nucleon, something like this. And we'll give A and Z as inputs in here. You can also again define this as integers. This is also an integer. And what you get is again a float from this. And then all you do is you return binding energy with some A and Z per nucleon. So you again divide it by Z. So that gives you binding, sorry, A. That gives you binding energy per nucleon because A is the total number of nucleons in the system. So now modify your program so that it takes just a single value of the atomic number Z and then goes through all the values of A from A equals to Z to A equals to 3Z to find out the largest binding energy per nucleon. This is called the most stable nucleus for a given atomic number. Hence, have your program print out the value of A for this most stable nucleus and the value of the binding energy per nucleon. Okay, so now let's get rid of this part. And what this says is that we just want to take an input of Z and we'll try different values of A, and we will find out for what value of A we have the highest binding energy per nucleon. And that is going to be the most stable nucleus given that particular atomic number. So given that particular element. So Z determines your element. For example, Z equals to 5 will be boron in that sense. Yeah. So let's try to do this. Has it asked for any particular Z? No, it's just, okay. So let's then print something else as well, def stable A. So we want to find out what is the most stable A for this. And we'll put in a value of Z, which is an integer. And this gives me as an output another integer, which is a value of A, which it is going to give me. And now what I'm going to do is I will start with a value of A where we find out the binding energy. So let's start with a value of for loop for A in range. So it says it'll start from Z and we'll go till 3Z. So it's 3 times Z plus 1. So again, the plus 1 is because we want to include 3Z. And for each of these, we'll finding out the binding energy, right? So we will do BE per binding energy. We'll call this the value of A, which has already been supplied, which is going through the loop, and the value of Z, right? And we find out let's call this energy, right? And this is, say, again, do the same thing. We call it energy old. And let's have something like energy new, because we are going to find out the old and new things in here. Okay. Or rather, let's just call this a numpy array. So let's call energy, and we'll use a numpy array. So we'll find out for all the values of z. So we'll do an np.zeros to start with, and this will be of the size same as from let's see, this is 3z times we are going to go from z to 3z. So this will be of the size of 2z, right? So what this would mean is that I want to create an array of zeros of the size 2z, right? Because I start from z and go till 3z, right? And let's call this I, comma a in enumerate. I'm going to explain what this means. And then what I'm going to do in here is I just do something like this, right? Okay, so this just actually I can do something which is even simpler than this. Let's keep the thing as simple as possible. So I start with a energy thing, which is a list, and do something like, then I do not even need enumerate, and let's not make this thing too complicated. Okay. And then I just call energy dot append and just do this, right? So what this would do is that I start with an empty list, and for every value, I start with value of z and go till 3z for different values of a, and for every value of a and every value of for a given value of z, I find out the energy, and that is what I append. And once I come out from here, I convert this. This is a list, so I convert this list to a numpy array. To converting a list to an array is just simple. I do something like this, right? And then what this is going to give me is just an array. The reason I converted the list to a numpy array is that then I can use the numpy functions. So I want to find out what is the maximum energy in here. So energy max, sorry, is np dot max of energy. So what this is going to give me is the out of all the array, it just finds out the maximum energy. And for that, I want to find out what is the value of A for this. And for that, I'll have to find out the position where I get this maximum value, right? So for that, what I'm going to do is do call it A max. This is where I have the maximum energy. And that I'm going to call np dot argmax, right? And this is going to pass energy into it. So what this is going to give me is the position where energy is maximum. So argmax is the position, and we know that we have started from zero, sorry, z. So z, we are going to a z plus. So this is basically the value of a where the energy is maximized, and then we can return. For example, we are going to return both energy max and a max. So let's first return a max and energy max. So we'll return this as a tuple. So anything between two braces with a comma is a tuple. So it's a collection of numbers. So this is what we are going to return. Okay. So now we'll try with some particular z. The program doesn't tell anything. So let's try something, say, and just to check if it is working or not. The question doesn't tell anything in here. So we are not just giving an integer. in here, as you can see, we are actually passing a tuple. So I'll just give something like, or rather, let's not have complicated things. So just give something like this. And this is something actually we don't need. We just need Amax. So yeah. And then let's not complicate this any further as well. Okay. So print. So what are we going to print? We are going to print the stable A. A for say Z equals to, let's choose some value of Z. Z equals to say 13. Aluminium. I guess 13 is aluminum, but I can be wrong as well. But as far as I can remember, 13 is aluminum. Okay. And for stable A for Z equals to is, and then we will call this thing stable A with Z. So I'm calling stable A with the value of Z, which I've passed in here. So it's the most stable A for Z equals to 13 is whatever this function is going to give me that. So let's run this. So it says that the most stable A for Z equals to 13 is 27. So you have A 27 and for Z equals to 13, right? Okay. So then let's go to the next part of the code. But before going this, I just want to make sure if everything makes sense in here or not.
Yes, so why are we using Armax here?
So if you, okay, let me step through the code in here then. Okay, so I have just turned the debugger on and went through the code. As you can see, this is like a array of energy is an array of 27 elements. And the reason it's an array of 27 elements is because we have started with like a value of Z and we went to value of 3Z. So we have 27 elements. So this is this array that you can see. And each of these gave you a binding energy per nucleon. So what we want is where the binding energy is largest. So we do an max, so that will give you the value. But if you want to know where in this array, the position where the binding energy is largest, then we give something called an argmax. So you, as you can see, it is, I think, this one, which is 14, which gives you the, I mean, the value is this 8.23, which you get if you pass max to it, to energy, you will get this value. But if you pass argmax, then it will give you the value 14, which means it is the 14th element. So that will corresponds to, this corresponds to Z. If you remember, we started with Z. So this corresponds to Z. Then this corresponds to Z plus 1. This corresponds to Z plus 2. Then this will correspond to Z plus 14, right? So that's why I have used argmax, and this is a Z plus in here. So that gives you the A. Yeah.
Yes, and then I mean in this right panel, and while describing the size of the energy thing, size of the energy array, it is shown 27 comma, and the second limit is not being shown. Like say, so here in the right panel, the size is written
Here.
as, yeah, 27 comma, and not the second thing. I mean in the above this panel.
Okay, okay, this one. Yeah, it just is a way Python says it's just a single array of just a 1D array. So that's why comma and you have nothing. So it's just a way of Python says that it's a 1D array of 27 elements. If this is a 2D array, then you will have say something like 27 comma 2. So then you will have like 27 rows and 2 columns in a sense.
Okay, so if it is 27 comma, then what does it mean? 27 number of the rows or 27 number of the columns?
Uh, for a like a 1D thing, it's just it shows like this, but it doesn't matter in 1D what is row and column because it's just a 1D array.
Oh, I see. So if this array has been represented like say in a different way, like say as a 27 number of the columns,
Uh-huh.
then this would have been represented as say comma 27 or what?
Okay, so if you want to represent this as like an array with 27, like a 2D array, you have to recast this, and then you can do something like a 1 comma 27 or 27 comma 1. Now, if you do something like a 1 comma 27, then it is one row and 27 columns.
Also, if I take the transpose of this energy and if I
You
dis
will you will
if I
actually not get anything because it is still a 1D array. So what then you have to do is something like this. Then it become like it is already energy is already a 1D array. And if you do something like this and you call this numpy array, right? Then most likely you are going to, let's see, we can test this as well. So then you can you see the difference. It's the same element. Now you got 1 comma 27.
why so?
Because now energy was already a 1D array and you have made energy come inside a box bracket. So now it becomes a 2D array.
Oh, I see.
And then it treats every element of energy as those many number of columns that you have passed. So now 1 comma 27 is like, if you look at it, it's one row and 27 columns.
Oh, so now if I take the transpose of this
Now
and
if
just
you take the transpose, this will work. So let's try that as well. Now you can say write test2 as test.t. So for taking transpose, you just write dot uppercase t. So then if you do, you see it's got become 27 comma 1.
yes,
And then if you look at it, it becomes like this.
yes,
But if it's just 27 comma, this is a 1D array. So transpose or doing transpose or anything doesn't make any sense, or calling rows and columns doesn't make. So you have, for a 2D array, you will know that it will always have two box bracket, unlike one box bracket. So as you can see here, in values you have one box bracket, while here you have two box bracket, and also in its size you see there are two elements.
yes,
And you can also test this. For example, there is something called, say, test.dim. This gives you the, sorry, ndim. This gives you the number of dimensions. So it gives you two, but if you give energy.ndim, you will get it one because it's a 1D array.
yes,
Yeah, so this is, I hope this is clear, is it?
yes.
Okay, okay. Let me then stop the debugging and let's move on to the next part of the same question, which says modify your program again so that instead of taking z as an input, it runs through all the values of z from 1 to 100 and prints out the most stable value of a for every element. At what value of z does the maximum binding energy per nucleon occur? Okay. So now we need to find out the energy as well. So let's modify this and also give the energy max, and then let's uncomment this. Now this is going to give me a tuple, and I'm not going to give anything in here. You can also give something like there is a tuple, but I'm not going into the complications of it. But yeah, you can go something like, say, tuple, and you can type something, but yeah, I'm not going into that right now. Okay, so now I'm going to do this and just go from for z in range. So it goes from 1 to 101 because we want to go from 1 to 100. And then it says I find out the stable A for every Z. So then what I do is I do the same thing, Emax, comma, Emax, let's call this like this, equals to stable A, where I just pass the value of Z in here. So this gives me Emax and this thing. And then at what, so this will now going to give me the most stable value of A for every Z. So let's first print that. Print uh, Z for Z equals to this, A equals to A underscore max. Right. So let's first test this. Let's not go till 100, but let's go till say 30, just to have a small number and have not so many prints, and then we'll move it to 100. So okay, so you see that for different values of Z, I get the most stable value of A. And yeah, okay. So now let's look at the last part of the same thing. At what value of Z does the maximum binding energy per nucleon occur? Okay, so here I have to also then find out, keep a track of Emax and also find out what value of Z do I have the maximum binding energy per nucleon. Okay, so then let's start with the value of 0, Emax global. So for all values of Z, I will be testing this, right? And now I will do something like if Emax is greater than Emax global, then I'm going to assign Emax global equals to Emax. Let's get rid of this. Okay. So what this says me is that if Emax is greater than Emax global, then what I'll have is Emax global equals to Emax. So I will go through all the Z's and I will find out what is the maximum binding energy. And at any point of time, if that maximum binding energy is more than the current maximum binding energy that I have found out till now, then I'll update to that. Otherwise, I'll keep it the same. Okay. And after the end of the loop, let's not then have this print statement for now. And what I'll print is max binding energy per nucleon is at, and we also have to keep track of the value of Z max global. This will also be 0, and here Z max global is Z. That particular value of Z is what we are going to give, is at, say, Z underscore max. Right. So this is what we do. Actually, we do not even need this value because it is only the value of Z which we are interested in. Okay. Oh, I missed putting it as a F string. Yeah. So let's run this. So the maximum binding energy per nucleon is at Z equals to 24. And yeah, so this is what this code gives. And I think you can verify this, but I think this is doing the correct job. Okay, so are there any questions on what has been done in here?
No, it's well understood.
Okay. So then let's move on to the next one. And let's see what's the time here. Okay.
So I have a query here that which precaution you take while writing programs in Python, like say, so that do we have something like say linters in Python, like say that there should be a space in between the operators and of and what is the philosophy of the Python to be followed while writing the programs? Cosmetic wise.
Sorry, I didn't actually get you. Can you Tell the question again.
Yes, so my question is that while writing the program, so are there guidelines in Python, like say there should be a space in between the operand and the operator while writing the program? Uh,
Yeah, the most important thing I think in Python is to mind these indentations. So everything under the same indentation is in the same code block. So that is, I think, the main thing. But rest is up to you of how you write.
okay. Like say in other programming languages, we do have linters, kind of a software, small software module. So as soon as I write the program and save the program, so that software will, in the background, will automatically adjust everything, the proper spacing, etc.
Oh, that thing. Okay. So there is something called black, which is like a proper coding style. So black is one kind of linter which you can run after you have written a code. You can pass it through black. So black is one sort of coding style which uh, reformats your code so that it is along one particular style or one particular format. So black is one of them. Yeah. So let me see if I can quickly give you an example of something like that. In fact, I have used black in one of my own repositories. Let's see. Like, this is something which I think if you are writing fully like a production code, which is a professional code, then you can use it. But otherwise, for small purposes, it doesn't make much of a sense. So for example, this is like something called workflows, which works with this. And then you have something called uh, a linter, which let's see if I have it somewhere. Yeah. So this is like some way in which it formats your code. Black is one kind of a formatter. There can be different other types as well. So this is something which I use, and this like you can just give black and the name of your Python file. So it is going to format you and adjusting for species. And if something is not in particular format, it can change things for you.
Okay.
Okay. So let's go move on to the next question, which is like about binomial coefficients. The binomial coefficients nk is an integer equal to this number, which is given. Now, using this form of for the binomial coefficient, right? I use a defined function of binomial nk that calculates the binomial coefficient for a given value of n and k. Make sure your function returns the answer in the form of an integer and not a float, and gives the correct value of 1 for the case k equals to 0. Right. So let's try this one. Again, let's get rid of all these. And let's call the function def. This is a binomial coefficient, and I'll pass n and k to it. This is an integer. This is again an integer. And what I will get is an integer. And this we have to explicitly make sure. Okay. So it is n factorial. So then we need something called the factorial of a number. So I will now will not use recursion, but later on since there is a question later on about recursion, which I will later on will think about. So for factorial, we do something like this. If n equals to 0, we know factorial of 0 is 1, so we'll return 1. Else, we are going to the next part of it. For I in range, and we'll call this number fact equals to 1. We'll start with a value of 1, and we'll go till n plus 1, and we'll start with 1. And we'll keep on multiplying. Fact multiplied equals to I. So what this is going to do is keep on multiplying 1, 2, 3, 4 until it hits n. And then we are going to return the fact, right? In fact, I think we can also get rid of this because it's automatically satisfied when we do this. Yeah, so we will start with a fact of 1, and if we give something which is 0, so it starts from 1 and ends in 1, so this part doesn't get executed and I get 1 in return. So just for the sake of verifying this, let's clear and let's do a for I in range 1 comma 1, say, and print I will expect it to print nothing. Yeah, that's what is happening. Okay. So now what I'm going to do in here is find out the binomial coefficient. So this will be factorial of n divided by, now I am using this 2, I'll come back, factorial of k times factorial of n minus k. Factorial of n minus k. Okay. And this is c nk is this. So what this does, this double slash does, it does an integer division. So let's see what, let me explain what this is. So say, for example, if you do 3, even say something which is divisible, say 4 by 2, what you will get is 2.0. So this becomes a floating point number by default. That is how Python behaves. Like whenever you have slash, which is a normal division, it always gives you a float. But if you do something like a 4 slash slash 2, then you'll get 2. So what you get as output is an integer number. And if something is not divisible, say if you do something like a 3 by 2, you get a 1.5. But if you do a double slash, you will get 1. So you only get the part which is not before the dot. So the decimal part is discarded and only you get the integer part. So since I want something which is integer, I, instead of having a single slash, I give a double slash because that's what the question asks me. Okay, so I have this binomial coefficient in here. So now it gives me some value so I can print it out and test it. So it gives the correct value of 1 for the case k equals to 0. So let's just test that then. Print, it'll print bin coefficient. So n, let's say 30 or something, and k equals to 0. For k equals to 0, it should give me something like a 1 to it. And let's see if I get that or not. So you see, I get a 1 in it. So this works. And now let's go to the next part. But before I go to the next part, is this part clear what I have done?
Yes, yes. It's clear.
Okay. So using your function, write a program that prints the first 20 lines of a Pascal's triangle. The nth line of a Pascal's triangle contains n plus 1 numbers, which are coefficients n0 and 1 up to nn. That's the first few rows is this. Okay, so let's then create another, give a value of n, which is the total number of values which are going to go in a Pascal's triangle. Say something, say here in this 1, 2, 3, 4. So it goes till 4. So I'll go for 4, but it can be anything. And now I'll get for I in range n. So for say n in range n. So this is n, and for k in range. So let's see, I'll move till n plus 1. So I start with something like n equals to, so this starts with the first one. So I'll start with 1 perhaps and can go till, so first element has digits in it. So it's 1 plus 1, which becomes 2, and then 2 plus 1, 3. Yeah, I think this is right. And then I'll go from k, which goes from 0 to n plus 1. So 0 to n is basically where I go to. And then I print the binomial coefficient. So this will be calling this function, and I give n and k to it. And I think it's the end that I give. So now what this does is tells the print statement to not go to the new line, instead just give a space. So then the print statement doesn't just go to the new line, but instead gives a space. And here, when I have printed all the k's, then only I want the print statement to just print nothing. What this will do is just go to the new line, right? And I think we are done in here. Yep. So we want one more line to be printed, right? So 1, 2, 3, 4. So since we go till 4, so we have to go till n plus 1 because we want 4 lines. And yeah, here it is. So we want the 4 lines, and here you can see that the Pascal's triangle is now getting created. So you have the digits 1 1 1 2 1 1 double 3 1 and 1 4 6 4 1. And now you can go as long as you want. Say you can even try some bigger numbers in here and do something like a 7 or something. And this creates a large Pascal's triangle. So this is mainly the idea. Okay. So is this part clear?
Yes, yes.
Okay. So the last part of this question is the probability of an unbiased coin tossed n times will come off heads k times is this binomial coefficient by 2 to the power of n. Write a program to calculate the total probability of a coin tossed 100 times comes up heads exactly 60 times, and the probability comes up heads 60 or more times. So this is just adding actually the elements in the Pascal's triangle, basically. So for the first thing is just if you want something which is exactly 50 times, what you do is, let's comment this part out for the time being. Is the first part is you want this to be exactly 50 times. So it's just your binomial coefficient of n is 100 in here. So you are tossing your coin 100 times. So this is your n, and you want to ask how many times it's 50. I mean, what is the probability that you have exactly 50 times that it's had? So then all you have to do is for k, you pass this value of 50, and to this you have to multiply, because the probability of having head is 0.5. So you have to do multiply 0.5 to the power of. So this gives you, sorry, k. So this gives you the probability of having a head exactly 50 times. But if you want to have probability of head 50 times, sorry, is it 50? It's 60. So it's 60 times. This is gives a probability, which I think is will be incredibly small. So prob, and you just print a probability in here up to say 0.3 0.1 E. Okay, so let's do this. There is something wrong with this. Let's see. What mistake have I done? Because yeah, probability cannot be more than 1, so there may be something wrong which I'm doing in here. Let's first check whether this is working perfectly or not. It should be bin. This is really a big number. Coin is tossed and times will come up heads. Exactly k times is this. Oh, sorry, it should be n. That's where I made the mistake. Yes. Yeah, so you can see that the probability is pretty low. And then the next part is finding out whether this next part is the probability that comes up head 60 or more times. So then that would mean is that for 60 times, we know it's k equals to 60. So we have to add 61, 62, go up till 100. So that's what we have to do. Then for that, we'll use the same formula, but just keep on adding all the probabilities. So let's have prob equals to 0 to start with, and then we will do a for loop. Yeah, for k in range. We'll start with, let's call it k start. So 60 or more times it says. So we'll start with k starts and we'll go till n plus 1. So that will mean till 100 n. And then your probability here will be just you keep on adding the elements of a Pascal's triangle essentially. And this is the value of k. Yes. And then we do this. Let's see. Hopefully this works. Yeah. So your probability has slightly increased, but yeah, because you have more number of cases in here, not only just 60, but 60 or more times. So your probability has slightly increased, but it's still pretty low because getting 60 heads or more than 60 heads in a toss of 100 is pretty rare. Yeah. So this is mainly the idea. Is this clear?
Yes, it's clear.
Okay. Okay. So let's go to the next exercise on prime numbers. So after that, we have something about this recursion, which you were asking, and we'll do recursion. But before that, let's do this prime number question, and let's then do the recursion thing. And I think, yeah, we have enough time to cover both of them.
Yes, so I shall view the question from the recording. I have written something in the chat.
Okay. Yeah, let me check that. Okay, okay. Okay, not a problem. Happy Teachers Day. Yeah,
Bye-bye.
bye. Okay. So let's go to this prime number thing. Write an efficient program to calculate the prime numbers using the following observation. A number n is a prime number if it has no prime factors less than n, and hence we only need to check if it is divisible by other primes. If a number n is not a prime number, is a non-prime number and is non-prime, having a factor r, then n equals to rs, where s is also a factor. For r greater than or equals to square root of n, then n equals to rs, which is greater than or equals to square root of n times s, which implies that s is less than or equals to root under n. In other words, any non-prime number must have factors, and hence, where was I? Yeah, must have factors and hence also prime factors, which is less than or equals to square root of n. Thus, to determine the prime, if a number is prime or not, we have to check its prime factors up to and including root n. If there are none, then the number is prime. If we can find a single prime factor which is less than root n, we know that the number is non-prime, and hence there is no need to check any further. We can abandon this number and move on to something else. So write a program in Python that finds all the primes up to 10,000. Create a list to store the primes which starts with just one prime number 2 in it. Then for each number n from 3 to 10,000, check whether the number is divisible by any of the prime numbers in the list up to root n. As soon as you find a single prime, you can stop with the rest of them. So yeah, I think I get the idea, and let's try to do this. So let's create a function def is prime. This is going to give you something which is prime or not, and give you the number n, which is an integer, and it just gives you Boolean as an output, which is true or false. So what we want to do is you start with something which is a square number which is less than square root of n, right? And see whether this is divisible or not. Okay, so if dot sqrt square root of n, and we make it integer. So let's say we start with something like 1, then square root of 1 is 1, and we're starting with something like 2, then square root of 2 is also 1. Similarly with 3 and with 4. Okay, so we do something like this. Is less than 1, then equals to 1, then return true. Else we go to this for loop. We will now check I in range. We will start, we know that 1 and 2 are primes to start with. So we'll start with something like 3 to so number we have to check the primes up to this. So we will check, we know that 3 is also prime. We'll start with then 4 and go till square root of n. So this will be integer of np.sqrt of the number that we give. And if n percentage I equals to 0, then we know that this is not prime because it has become divisible. We will return false. While if we have come out and we have not got it, then we have not found any prime factors, then we will know that this number is actually prime, and then we are going to return true. Okay, so now let's move on and try to test this with a few numbers and see if this is working or not. Okay, so print is prime, say 1, 3, 4, 5, 6, 7. So let's try a few numbers like 2, 3, 4, 5, 6, 7. So all are calling it is prime. So something must be wrong in here. So let's see. So let's give a breakpoint in here, clean these, and let's see where we are going wrong. So we come in here, square root of 1 is less, this is true. This returns true. Okay. Did not want this one. Here until the next breakpoint. So now we come to n equals to 2. Again, it returns true. And now with 3, again, I think it prints 3. So now we come to 4. In here, this is 4. So 4 has to be divisible by 4. Oh, so the mistake is we want to go till square root of n. So yeah, this +1 is something which I've missed. So let's stop this and try to run this. Still there is a problem. Let's try to figure this out. Three with 4, we come in here. So we start with 4 and we go till so we have to start with say 3, I guess. Because if we start with 4, then this is let's see what this thing gives me. This gives me 2, so 2 plus 1 is 3. So this will not work out. So let's go the other way around. We start with this one number and go till 2 and -1. So let's stop this. thing in here, and let's do a percentage clear just to make sure how the for loop is working in here. Say for I in range 3 comma, say start with 5, go till 2 minus 1, and then print print I 543. So you do not include the last number. So yeah. So then if I do not include the last number, I have to go till 2. So all I do in here is this thing, and let's see. So 1, 2, 3 are true because these are prime numbers. Then 4 is false because this is not a prime number. Then 5 is a prime number, it's true, then false, and then true. So I think this is working fine. We can go the other way around as well. So we can check, start a check from 2 and go till the end. Now let's see if this works or not. We can start the check from 2 and go till the end. This might also work. It just goes the other way around. And let's see, true, true, false, true, false, true. Yeah. So whatever you do, you start from 2 and go till square root of n, or you start from square root of n and move till 2. Whatever you do. So I think this is passing the test of is prime now. So now, right now, what we can do is we go to the next part of this code, which is if you find for each number, then for each number 2000, check whether the number is divisible by prime and add it to the list. Okay. So prime numbers, and we call it 0. And for I in range from 3 to 1000, as it says, so we'll do 1001. Sorry, 10,000. So one more 0. So we'll do 10,001. And then you can do if is prime I. So that will tell that if I is prime or not. Then we do prime numbers dot append I. And at the end, what I'm going to do is just print the array of prime numbers. Right, and just do this. So you see, we got the list of all the prime numbers in here. So it's 3, 5, 7, 11, 13. So as you can see, this list works very well. And we got the list of all the prime numbers. Okay. So now we are into recursion. And I think this is going to be the most likely the last question that we are going to solve today. And this is a tricky thing and may not be clear initially at first. So I would also ask if there is something which is not clear to please clear it up in the next class or after this, asking questions, and we'll then again resume after we have discussed recursion from the next day. Okay, so let's do. So recursion means calling a function within the function itself. So let's clear the screen and clear all these things up. And okay. And this is one way of having things in a loop, which is calling a function within a function. And let's see what we can do, how we can achieve that. A classic example for this is factorial. So if you want to find the factorial of a number, then it is, say, the factorial of n, say factorial of n. You can write this as equals to n times the factorial of n minus 1. So here you can see one function is written with some argument is written in terms of the same function itself. So recursion is when this classic thing is followed, that if you can write the result of a function with respect to the function itself. This is exactly what we are going to do in factorial. So let's define a function called fact of n, which is an integer, and what I'll get is also an integer. And then let's go in here. Oops. Okay. I'll cut this down. Tab in here. Okay. And now what I do is if n equals to 0, if it is 0, then we are going to return 1, right? Else we are going to have this, where fact of n is what we are going to return, n times fact of n minus 1, right? So this is exactly now what we will do once we get the factorial of a number, and this is going to work pretty well. So let's do a print of fact of, say, 3. So I know that with fact of 3, you will get something like a 6. So here you see you get 6. So if you get fact of 0, then obviously the first is satisfied, and then you get 1. For doing a fact of 1, you will get 1. For doing a fact of 2, you're going to get 2. So I think this is working. And now we will do the same thing for getting something called Catalan number. Remember that we have already achieved Catalan number before by not using recursion in the previous question, in one of the previous questions. So now here we are going to rewrite the Catalan number using recursion. So let's create another function, def Catalan, and let's give it a value of n, right? Now if we know that if n equals to 0, then it is 1. So if n equals to 0, then return 1 to it, else we are going to return the value of whatever it is given in here. So this is again return, let's type the thing. It is 4n minus 2, so 4 times n minus 2 by plus 1 times, we call it Catalan of n minus 1, right? So this is how a Catalan number would work, and this is now we will be using this for finding out the Catalan number of for n equals to 100. So for that, we just give a print and just call Catalan of 100, right? And here's, and this is what we are going to get, a huge number, but this is exactly what the Catalan number is for 100, C of 100. Okay, so the thing to note in here is that in many cases, as you can see, you can either use for loop or you can use recursion for getting something called uh, these kinds of relations where a function can be expressed in terms of some other function. If you are extremely interested, I would ask you to check something called Ackermann functions. These are kinds of purely recursive functions. So for these functions, there is no other way for expressing or finding out the value of Ackermann functions without using recursion. So these are called purely recursive functions, which an Ackermann function is one of the most simplest of such examples of purely recursive functions. Yeah, this is something quite advanced, and I'm not going to talk anymore about it. And if you're interested, please go and check it out. It's called, just to spell it out, Ackermann function. Yeah. Okay. So let's go to the last part of this recursion question. It says, Euclid showed that the greatest common divisor of g of m and n of two non-integers satisfies this. Write a Python code, a Python function that employs the recursion to calculate the greatest common divisor of m and n using this formula. Yeah, use your function to calculate the greatest common divisor of 108 and 192. Right. So let's call this def GCD then, and we want to find out for m and n. So we give m, which is obviously an integer, n, which is also an integer, and what I'll get is also an integer, right? That is what this thing is. And now here the first part is this: if n equals to 0, then I'll going to return m, right? Else, go to the next part of it, that we are going to call return GCD itself with n and m modulus n. So we'll do m modulus n. Okay, so we return a GCD of n, comma m modulus n, right? So once we have done this, we just give a print and try to find out the GCD as asked in the question of 108, comma 19, right? And enter. So it's 12. So let's verify this. That's just by doing a simple Google search, that whether we have found out the correct thing or not. Let's GCD of and calculate, and indeed it is 12. You see, we get the value of 12. So I think this works. So let's move back, and this is also an example of a function where you can do this. So then let's move to the last part of this, where it says comparing the calculation of Catalan numbers in part A with that in Excel 1.7, we see that it's possible to do the calculation two ways, either directly or using recursion. In most cases, if a quantity can be calculated without recursion, then it will be faster to do so. And we normally recommend taking this route if possible. There are some calculations, however, that are essentially impossible, or at least more difficult without recursion. So, and this is exactly what I was talking about when I was talking about Ackermann functions. Yeah. So another classic example which you can try with recursion is the Fibonacci pattern, where you have a recursion where you have two numbers, and the third number is like every number is a sum of the predecessor and the predecessor of the predecessor. So the last two numbers add up to create the next number. That is also an example of a recursion. And turns out you can also express this in terms of a n, and you can solve this, but the most simplest and straightforward way is using recursion in a Fibonacci pattern. Okay. So I think this is what I am going to discuss today. And I am going to end the class here, because now if I start with the next question, it will spill over the stipulated time, which I do not want right now, because that will be, I think, too much for one class. So this is where I would like to end. And I hope you had a good time learning and listening to all these things. And until next time, Take care and goodbye.